Bismillahirrahmanirrahim. Hello everyone. My name is Azmat Ali. I welcome you all in class of real analysis. In the last lecture, we discussed about rational and irrational number system, and further, I discussed an example 1.1 from the book Principle of Mathematical Analysis, written by Walter Rudin. So, in this complete course, I will follow this well-respected book. Example 1.1 is show that there is a no rational p that satisfies the equation p square equal to 2. Its equivalent form, or another way to write this equation, is that show that square root 2 is an irrational number. Is an irrational number. In today's lecture, we will discuss two important topic. One is order on a set, and second is ordered set. To define these two terms, I will follow this book. So, the definition of these two terms in the context of this book are: firstly, we define what do you mean by the order on a set. Actually, the summary of this lecture is simply a word. Order on a set means a relation. A relation. So this word shows the summary of this lecture. Order on a set mean a relation on a set. So the order on a set a non-empty set S, is a relation, and here in this book the author used the symbol for relation is less than sign. This less than sign is represent here a relation, order relation, if it satisfies the following two axioms. Order on a set is a relation less than, denoted by less than sign, if it satisfy following two properties or axioms on S. The first property is, for all x, y belong to S, either one of following things called: either x is less than y, or x is equal to y, or y is less than x. This is the first property, first axiom of order on a set. The second axiom is, that is the transitive property: for all x, y, z belong to S, if x is less than y and y is less than z, this implies x is less than z. So if a relation less than sign satisfies these two axioms, then we say that this less than sign, that is actually here a relation called order on a set. And the set in which we can define an order is called ordered set. A set in which we can define an order relation is called ordered set. that is written in order pair form as the set S with the order relation. So this shows that uh, S is order set with order less than sign. Now I share here some examples in which I will elaborate the concept of this order relation. In sometime the this relation less than sign has its usual meaning that we use in routine mathematics. That when we say one number is less than the other in that sense, but it is not necessary that always this less than sign always shows its usual meaning. There are many examples in which less than sign does not show its usual meaning. Actually, less than sign in this book only just represent a relation sign. For example, if you read set theory or discrete mathematics, we say that if there are two elements A and B in some set A, we call A and B. A is related to B. We write them as A or B. R is the relation which can be defined with some conditions. For example, we say A is related to B if B minus A is divisible by 6. Divisible by 6. So here R is used as an relation. You may use uh, greater than sign as an order on a set. Because I am discussing the definition of order set from this book. So I am following this book, and in this book, less than sign is used for relation. So now we share some examples that will elaborate the concept of ordered on a set. For example, for example, and we say that the set of real number R with this less than sign is an order set if order relation is defined as A is less than B if B minus A is positive. So we need to check whether R is an ordered set with this order that is the less than sign. Now you can observe that here the less than sign has its usual meaning. The first axiom is that for any two real numbers from R, either one of the inequality will hold. We know one of the expression will hold. Either first number is less than y, less than the second, both numbers are equal, or the second number is less than first. So it is obvious from the given definition A is less than B. The second axiom is for any three numbers, for all A, B, C belong to R, we need to show that if A is less than B and B is less than C, this implies A is less than C. So our target is to check that whether A is less than C. Now, when A will be less than C, for this we will show that C minus A should be positive. This is our target. So So as A is less than B, this implies B minus A will be positive. And B is less than C, this implies C minus B is positive. We need to show that C minus A is positive. Consider consider C minus A. By adding and subtracting the second number, that is E here, we have C minus B plus B minus A. Now, from above here, B minus A is positive, C minus B is positive. Both the expressions are positive here. Sum of two positive number is always positive. This shows that C minus A is positive. As both axioms of order on a set are satisfied, so this relation is an order on a set of real number R, and the set of real number R is an ordered set with this relation. Now, whether the set of complex number is also an ordered set with the same relation, whether the set of complex number C with this relation, that is the less than relation is here, and we say that Z1 and Z2 are the two complex number. Z1 is less than Z2 if Z2 minus Z1 is positive. So my question is that whether the set of complex number with this order relation is an ordered set if less than sign has the same meaning as it has a usual meaning. As you know that set of complex number does not satisfy the order axioms. In short words, we know that set of two complex number are not comparables. We cannot say that, for example, if one first complex number is 8 plus 2 iota and second complex number is 4 plus 8 iota, can we say that Z1 is less than Z2? Or we can say that two complex number are positive equal, or we can say that Z1 is greater than Z2. There is no tool to compare any two complex number. So in short, we can say that the set of complex number with this less than sign, or with, that is actually here order relation, is not an ordered set. So complex number with less than sign is not an ordered set, whereas the set of real number with this less than sign is an ordered set. Uh, the third one example that will elaborate the concept of order on a set more precisely. Suppose that P of A is is power set of set A. As you know that power set of A is the set of all subsets of A. It is the subsets it is a collection of all subset of A. We say for any two sets A and B belong to power set of A, set A is less than B if A is subset of B. Check whether this power set of A with this order relation less than is an ordered set. Is an ordered set. Now you know that in our usual routine we cannot say, we can never say that first set is less than the other. first set may be the subset of the other, or second set may be the superset of the first. But we not use the term first set is less than the second number, because second set, because A and B are actually sets. These are not numbers. So now you can observe that this less than sign, that is actually subset equal relation. This less than sign actually shows here subset equal relation. Okay. So I want to say that this less than sign is not always represents its usual meaning as we use in routine mathematics. It just represents the relation between two elements of a set. So to check whether this set, power set of A with this less than sign, is an ordered set or not, this less than sign is said to be ordered on a set if it satisfies the two properties. The first property is, for any two elements, for all two elements AB belong to power set of A, either one of the expression will be hold. First is A is less than B. It means A is subset of B. A equal to B, and second is A is greater than B. Mean to say that, in other words, B is less than A. That is B is subset of A. So whenever you will choose any two set from power set of A, there will be only one condition. Either first set is a subset of the second, either both sets are equal, or either second set is a subset of first. So first axiom hold. Second axiom is transitive property. That is, for all ABC belong to power set of A, if A is less than B and B is less than C, this implies A is less than C. It is A is less than B means A is subset of B, and B is less than C means B is subset of C. So this is obvious. When A is a subset of B, B is a subset of C, then obviously first set will be subset of the last set. This implies A must be subset of the last set C. So this shows that this power set of A is an ordered set with order relation less than. So I hope today's lecture was helpful for you, and the things that we have discussed so far are clear now. Inshallah, in the next lecture, we will discuss about ordered field. Okay, take care. Allah Hafiz.